In this video, I want to start talking about integers and their behavior under division. And this is, in general, this is called the number theory. So the first thing we're going to talk about is something called the quotient remainder theorem. And the idea is when we divide one integer by another, we always get a unique answer with some remainder that's less than the divisor, what we're dividing by. So let's talk about this more precisely. Let's say we have two positive integers. Then there exists unique integers q and r such that we can write a as q times b plus r, where r is some remainder. So r is between 0 and b, inclusive of 0, exclusive of b. So you're thinking of q as your quotient and r as your remainder. And just to make sure we understand what's going on, so if I have a problem like 25 divided by 4, well, I know that that is going to be 6 4s are 24, so 6, remainder 1. So that means I can write 25 as 6 groups of 4 plus that remainder of 1. So here is my q, here's my remainder r, and of course my a and my b are here. We usually call a the dividend, b the divisor, and q is the quotient, r is the remainder. Okay, so I'm not going to talk about the proof in general for this. I just want to kind of sketch it. I want to give you a flavor of what's going on here. So, first of all, there's two things happening. The first thing is we say that there exists these two integers, q and r. So we need to show they indeed exist. And that's the first part. The second part, to show that they're unique, that there's only one way to do it, that'll be done as an assignment question in the future. So the idea of the proof is like this. So take your a and your b, and you're treating q right now as a variable. So this set, capital A, is going to be all numbers of the form a minus qb, so q is some whole number, and we only want the cases where a minus qb is greater than 0. So let me just do this by example here. So the a for this set here, remember, the dividend is 25 and the divisor is 4. So we're looking for all things of the form 25 minus q times 4, where q is a whole number, and of course our expression 25 minus q times 4 is indeed greater than or equal to 0. So that's the set capital A for this example up here. Well, what does this look like? Well, this looks like when q equals 0, we have 25 minus 0 times 4, so 25 minus 0 is 25. So that's when q equals 0. We have when q equals 1, this is going to be 21. When q equals 2, this is going to be 17. Then we have 13. Then we have 9. Then we have 5. Then we have 1. So that's when q equals 0, 1, 2, 3, 4, 5, and 6. So, if you remember from way back in chapter 4, when we started talking about induction, we talked about the well-ordering principle. So, and it basically said that any subset of the natural numbers has a least element. And, well, this is a subset of the natural numbers, or you could even make it the whole numbers, doesn't really matter. This indeed does have a least element. Our least element here is this guy, it's 1. Here's our least element. So, there's our least element. And once we have our least element, the least element is going to be our remainder. This is our remainder, r. And the q that gives us that least element, that's our quotient. So this 6, when we plugged in q equals 6, that gave us our appropriate quotient. So we know we can always find a q and an r so that this works via this argument. But the next thing we want to show is that, well, there's only one way to do this. There's only one q and one r, where we can write a to be q times b plus r, where r is a proper remainder. So that's what we're going to show in our next assignment. And that's called the quotient remainder theorem. But you can expand this a little bit. In some sense, there's nothing special about things being positive. We can make things negative as well. So here, let's say we have two integers. So they're not positive, they're just two integers, a and b. The key is, and I wrote this kind of backwards from above. It's not incorrect, but just to match up with above, I'm going to switch the role of the a and the b here. We'll have b as our divisor and a as our dividend, but it's the same idea. Okay. So a and b can be any integers you like, except you can't divide by 0. So we're going to say b can't be 0. Then the same thing holds. There exist unique integers, q and r, so that we can do the same thing, where r is a proper remainder between 1 and, well, we said here b could be negative, so we'll just take the absolute value of it. So the proof of this I'm not going to get into. We'll just omit this, but it's the same idea as the proof above. But let's use this. Let's find q and r in the theorem above. Okay. So here we have a is 15, b is 4, so we're looking for 15 divided by 4. What is that in quotient remainder form? This one is pretty easy, of course. Well, 4 into 15, so that goes 3 times with a remainder of 3. So 15 equals 3 times 4 plus 3. So our q is 3, and our r is also 3. Let's look at negative 34 divided by 6. So we'll do that over here. We have to be a little bit careful when it comes to the remainder, because remember, the way we're going to write this is the remainder is always going to be positive. It's going to be between 0 and the absolute value of the divisor, inclusive of 0, exclusive of the divisor. So in this case, our remainders are going to be 0, 1, 2, 3, 4, or 5, and we're dividing by something positive, so that's pretty easy to see anyway. The next time it won't be. Okay, so let's go ahead and look at this. So, in some sense, you'd be tempted to do this. You'd be tempted just to go 6 into 34. Well, 6 goes into 34 5 times with a remainder of 4. So you'd be tempted to say that negative 34 is negative 5 times 6 minus 4. But remember, this is not really what we're looking for here. This isn't the proper remainder. Remember, our proper remainders are between 0 and 1 less than the divisor. But there's not too much we have to do. Let's just add 6 and subtract 6 here. So let's do that. So this equals, well, here is negative 5 6s. Here's another negative 1 6. So in total, I have negative 6 6s. And then to get that remainder that I want between 0 and 5, inclusive of both, 6 plus negative 4 is 2. So in the first case, we had Q was 3, R was 3. In the second case, we have Q is negative 6 and R is 2. Okay, let's continue here. Let's do 3. I'll do it down here. So we want 82 divided by negative 13. This is 3. Maybe pause the video, see if you can reason this out. Give it a go. Okay, now that we're back, maybe at first I'll just draw some lines here so it's easy to see what's going on here. And then 3 is going to be down here, of course. Okay, in this case, we're going to have to be a little bit careful. So we know that 13 goes into 82, and you can check. This goes exactly 6 times with a remainder of 4. That's 78. 4. Okay. So, what does this mean? Well, this means that 82 is 6 times 13 plus 4, that regular old division. But I want negative 13 here. So I can write this as negative 13 and change this to a negative 6. And my remainder here remains positive. So this guy, when we have a positive dividend and a negative divisor, well, this is going to be that 82 equals negative 6 times negative 13, that's 78, plus 4, that's 82. So it's a little bit easier in this case maybe than case 2, because your division gives you the answer. But thinking this through every time allows you to kind of avoid just memorizing rules, and I think that's very important. Let's do 4. Again, try it yourself. Pause the video. Note we have both a negative dividend and a negative divisor. Okay, so now that you're back, let me make a little bit of room here. I'll just erase this side working. So let's go ahead here. So we want 8 into 55. But remember, we're going to end up being negative. 8 goes into 55. We can see that this goes in 6 times. That's 48. With a remainder of 7. So if this was positive, we'd get 55 equals 6 times 8 plus 7. So we're tempted just to say, well, it's negative 55. So this is going to be negative 6 times 8 plus 7, just taking the negative both sides, which is, of course, negative 6 times 8 minus 7. But remember, we want two things. We want a proper remainder, which we don't have anymore, and we want this to be negative 8. So let's do both. Let's get that proper remainder first. I'm going to add and subtract 8. And so negative 7 plus 8 is 1. And here's negative 6 eighths. Here's another negative 1 8. So this is negative 7 times 8 plus 1. And we're almost there. We want a negative 8 here instead of a positive 8. So let's just flip the signs of both of these guys. So this becomes 7 times negative 8 plus 1. And you can check this works. 7 times negative 8 is 56. Negative 56. Negative 56 plus 1 is negative 55. So it looks like we did it. So here we have that negative 55 divided by negative 8 gives us the following expression. Negative 55 equals 7 times negative 8 plus 1. So here we have the quotient is 7, and the remainder is indeed 1. So just like all of the other ones, we can write down the quotient and the remainder, given if either the divisor or the dividend is positive or negative. It doesn't really matter. Both of them can be positive, both can be negative. One can be positive, one can be negative. Doesn't matter. We can still figure it out using this quotient remainder theorem. The big thing is you need to make sure that you're having an integer number of groups of your divisor and that your remainder is between 0 and the divisor minus 1 in absolute value. So that's what's going on here, that it's a proper remainder. Okay, just a quick note about a little notation here. If we just want the remainder, we'll write it like this. We'll say we want A mod B. And if we just want the quotient, we'll write A div B. And mod means modulus, whatever that is. And div, I guess, just means division or something like that. Okay. Maybe it's a good idea to make sure you know how to use this notation by practicing with the 4 examples we just did on the previous slide. So pause the video now and see if you can work out what A mod B and A div B are for the previous examples. Okay, so here are all 8 things we want to work out. Well, 15 mod 4, that's the remainder when you divide 15 divided by 4, so that's 3. And the quotient was 3, since 15 equals 3 times 4 plus 3. The mod is the remainder, and the div is, of course, the quotient. Okay? Negative 34 mod 6, well, we said that was 2, and negative 34 div 6 is negative 6. 82 mod 13, we said was 4, and 82 div negative 13, we said was negative 6. And finally, we have that negative 55 mod negative 8 was 1. That's the remainder. And div, the quotient we said was 7. So that's just practice using the notation. Div doesn't come up that often, or at least it doesn't come up as often as mod. Remainders are very important. We kind of hinted at that in the previous section when we were talking about equivalence classes. Remember, we had that dn equivalence relation, and we said two numbers were related exactly when they had the same remainder when you're dividing by n, and that's going to be really important for us. So note here, and this is important, if you have some number a, then it's going to have some remainder r when you divide it by b. I should say, let me say here, mod b, just so that's a little more clear. So if you add extra copies of b to it, then it's still going to have the same remainder. And that's what we talked about up here in the previous video with that dn equivalence relation. So we can show, this should be for, not of. We can show for when a mod b equals c mod b, which equals that remainder r, then a and c belong in the same equivalence class when dividing by b. And we called this relation before. We called it dn, but usually it's written either like this. So we'd say the equivalence class of A is related to the equivalence class of C mod B, like that. So that's how we'd read that. And we'll explore this in a second. So before we go on and look at this a little more precisely, I want to do a few more examples with it, just to make sure we understand what's happening here. So let's define what congruence modulo some number is. We're thinking of n here as our divisor. We're thinking of this like our divisor. And so we're going to pick three integers, our divisor n, which is greater than or equal to 2. And I will say this choice, greater than or equal to 2, is one that lots of books make. But you don't really need it. So, popular but unneeded condition. Really, all you need is that n is a whole number and this whole thing can still work. I'll just say this, but if you're dividing by 1, then it turns out that all numbers will be congruent to each other. And if you're dividing by 0, it will turn out that no numbers are congruent to each other. But to avoid those kind of special cases, lots of books just say, well, our divisor is going to be greater than or equal to 2. So we have these integers, a and b, and our divisor here. We say a is congruent to b modulo n, or mod n, if n is a factor of a minus b. Just like in that video before, if a and b are related with that equivalence relation dn that we talked about. And we write that either a is congruent to b with mod n in brackets like that, or another popular-ish notation, it's getting to be more popular, is you use this congruent symbol with a little subscript n in between them. It's like an equals, but it's saying a and b are congruent mod n. These notations mean the same thing. So what does this mean? If you remember from the previous video, we showed that, well, it means that A and B definitely have the same remainder. Those remainders cancel out when you subtract them. And it also means that A and B are in the same equivalence class, and the equivalence class that they're in is one that can be represented by that remainder. So this is the remainder of A and B. It's the remainder of A, and it's the remainder of B. And what we can do is we can just say, well, the thing that's nice about equivalence classes is there's finitely many of them in a lot of cases, and we can study some numbers just by studying representatives from the equivalence class. So I'm going to define something here. It's usually defined like this. It's called Z sub n, and it's the set of equivalence classes of numbers from 0 to n minus 1. And you're thinking of remainders when you divide by n. And also, sometimes if it's unclear or people really want to highlight what the divisor is here, they'll put a little n as a subscript to the equivalence classes. And that is Zn. And the nice thing about these is we can work with the equivalence classes themselves without having to worry about infinitely many elements. And that's really nice. And that's what we're going to show later on. So we'll do things like add equivalence classes together, multiply equivalence classes. So we see some really powerful stuff here using the equivalence class idea. And just as a quick little example to make sure we understand what's going on, let's say we were interested in what Z7 was. So maybe pause the video, write down the equivalence classes inside Z7, then tell me to which equivalence class do the following belong. So let's do 10, negative 11, negative 1, 23, 704, and negative 596. So pause the video, give this a go. Okay, now that we're back, well, we're in Z7, so the equivalence classes are, and I'll put this little 7 subscript in, 0, 1, 2, 3, 4, 5, and 6. I'll put my little 7s there. Again, that's just highlighting that we are working mod 7, where we're dividing by 7. So, well, we just need to figure out the remainders of these numbers to determine what equivalence class they're in. That's the key. Okay, so, well, the first one is easy. 10 is 1 times 7 plus 3. So 10, it's an element of the equivalence class of 3. This is all numbers that have a remainder of 3. Okay? Negative 11, and you can check to make sure that you have this correct. But negative 11 is negative 2 times 7 plus 3. So that's also in the equivalence class of 3. So negative 11 is another element in there. And you can check that those are indeed related. What is 10 minus a negative 11? Is that divisible by 7? In fact, it is. That's 21, which is, of course, 7 times 3. Since we subtracted these two numbers and we got something that's divisible by 7, they're in the same equivalence class. Okay, let's keep going. Same ideas with the others. Here we have negative 1 is negative 1 times 7 plus 6. So negative 1 is an element of the equivalence class of 6. What about 23? Well, 23 is 3 times 7 plus 2. So 23 is an element of the equivalence class with the representative 2. And again, I just picked these because they're the remainders, but we don't need to have 0 here to say it's the equivalence class of 0. We could have any representative, so any number that has remainder 0. We could have 7, 14, negative 7, 70, whatever. Let's keep going. 704. Well, that's pretty easy to see. That is 100 times 7 plus 4. So 704 is in the equivalence class of 4. And negative 596, well, maybe there's a little thinking here. But we know how to determine remainders from the previous slides, so we can just go ahead and do it. And we should get minus 86 times 7 plus 6. So negative 596 is in the equivalence class of 6. And just as a reminder, this is the element symbol there. It's a little bit messy because it's written on its side, but hopefully that's clear. That's what it means.